Welcome back. We're going to do a quick little demonstration of how we can do overflow in the different data types when we're working with recursion, as well as just the idea of integer and double overflow. We can see what happens with that. So as you can see right here, my overflow demo method, I'm calling on my start method. And overflow demo, I'm using just a loop to iterate from 0 to 200. And I'm calling either the calculate factorial int version or the double version. And we can have the same name of a method simply by passing a different parameter signature. So in this case, I pass it index as an int, and then I pass this one index times 1.0 to get the double value. And so Java will automatically call the correct version of the method based on the parameter signature. So I have my int version up here. If source is equal to 0 or 1, I return 1. Otherwise, return calculate factorial, passing it source minus 1 times source. For the double version, it's a little bit different though. Because I can't compare direct equality with the double type, I have to actually make sure it's close enough. So in this case, I have math.abs and I pass it data minus 0 and is less than 0.0001, or math.abs of data minus 1.0 is less than 0.0001. So making sure that they're close enough, because I can't know exactly what's inside a double value simply because the way that we store the mantissa of the information, what happens beyond the specified value of our double parameter in this case, we don't know enough beyond that, so it could be a little bit less, a little bit more, we don't know. And so because of that, I have to use the magic power of math.abs and use a subtraction on that to make sure I'm close enough to the actual value I'm looking for. But other than that, the logic is the same. I return 1 in that case, otherwise return data times the calculate factorial. Same thing right here, just in a different direction. That doesn't matter actually in the amount that I'm actually doing with it. It's just where does the breadcrumb lie on the recursion path. So I'm going to run that through there on the overflow demo. We can see what happens with those results. We can see how effective it is to use an int for a value versus how effective it is to use an to use a double for the value, and see what happens as we get close to the max value of those different data types. So let's go ahead and we'll run this code for us really quick. And as I run the code right here, you can see down at the end of this, when I'm at 199, I have 0 and infinity, which is, oh, that's a little bit interesting. I have a value of 0 versus infinity. And so if I scroll up here, we can see, oh, here is when I run out of double. I run out of double when I call the factorial version of 170. I'm at 7.25 times 10 to the 306th, which is redonkulously huge. There's only times 10 to the 81st-ish or 86th, depending which count you're looking at, for atoms in the universe. And so times 10 to the 306 is huge. So we have up until that point, and once we get beyond that 10 to the 306th power, we're in the realm of infinity. So we're huge. We're really, really big. And so double actually supports the idea of both positive and negative infinity, as well as the concept of being both positive and negative infinity at the same time, aka nan, or not a number. And one of the cool things about nan is not equal to nan. Oh, I know, pretty cool. However, we've got that 0 value for the int. Int is 0, 0, 0, 0, 0, 0, 0. Keep going all the way up here. Keep on going. Scroll, scroll, scroll. Look how long we have to go until it's at 0. And we can go and wait a second. Negative 2 billion, negative 898 million, 1 billion, negative 2 billion, negative 1 billion, whoa, back, forth. And so when we're talking about the idea of integer overflow, which is what's happening right here, I'm pouring so many values into my int bucket that it flips over and becomes negative. And then I pour it back into the negative and I add more, and it wraps around to positive again. And it goes back and forth. But at some point, in this case right here of 34, it's so big it can't even be fit into a double value at all. So just stuck at 0. Like, I can't go beyond that. Plus or minus 2 billion, I'm in 4 billion in change land. It doesn't matter how much you add to me, I'm going to be out of bounds no matter what. And so at that point, we're simply just stuck at 0. And so the idea of overflow is when I put a value into it, we can see it happening up here. So, 40, then 362, and then 399, 47, 193, 127, 2 billion, 2 billion, and then negative 2 billion. I added so much to that 2 billion and change that it flipped over and it became negative. And once I hit that point, it just goes back and forth along that path, going positive, negative, positive, positive, negative, positive, whatever, and it can't actually hold any information. So we have to make sure we use the correct data type when we want to keep the information, actually use it. And so because factorial grows so fast, we have to actually keep that in mind when we're looking at it. So we see the fact that we have a huge growth rate right here. And so we see the idea of integer overflow very early on. Double doesn't overflow until we get down to 10 to the 306th power, which in the case right here is about factorial of 170. And so once we get past 170, oh, we're out of bounds, and then we get infinity. So it actually tells us more information than the int version does because we're still using actual numeric values. And so by doing that, we're able to display that information by simply calling the calculate factorial. We can see how fast it grows and how amazing it is, and see what happens when we actually try and compare those values on that. And once we get past 170, we're just simply stuck at that, and we're good to go. Hope this is helpful in understanding how integer overflow works and what happens when we exceed the bounds on a double as well, and the difference between those two. Hope it's helpful. Cheers, and have a great day. See you next time. Bye-bye.